All right, welcome back. We are doing lesson 6.9, which is called Water Wheels and the Unit Circle. And so here we're practicing. So whenever it says practice, that means we've learned a couple of things and now we're going to practice and get better at something. So if you look here, it says quick graphs. And it says in the previous lesson, you learned how to graph sine, cosine functions using the number values along with the x-axis to represent the angle of rotation. Of course, in our Ferris wheel model, we still want the x-axis to represent time in seconds. And now we have the possibility to describe the angular speed of the Ferris wheel in radians. So you're going to work with a partner, and we'll do this in class, to sketch a graph of each of the following functions on the appropriate grid. And you need to show one complete period. So choose your grid wisely. And you can find the one that looks the most like the can you find the one that looks the most like the Ferris wheel equations, right? So I'm going to show you how to do one of these. That way when you're together with your group, it's a little bit like it makes just a little bit more sense. Okay. So you have to show one rotation. So think about Carlos going all the way around the Ferris wheel and coming back to that same point where we started at. So it says, use the quick graph strategy, plot points along the midline to define a period, and then plot the maximum and the minimum to define the range. So whenever I do this, you should know what all of these kind of like numbers mean. But if you don't, just kind of like follow my lead here. So, okay. So the very first thing I noticed is that this is a +4. So this is going to be your midline. So I'm just going to draw in a very light, let's see. Oops, I don't need my thing. Thanks. Kind of like this. So this is going to be my midline here. So if you can kind of like pretend that's your midline, that would be good. And then what I'm going to do is I'm going to look at how high it goes and how low it goes. So my midline comes from that number there. My high and low number comes from your amplitude number, which is this number here. So can you go up to and down to from your midline? And that's where your function is going to live. So it's going to go as high as here and as low as here, right? And this right here comes from our 2, which is our A. It's our amplitude, how high and how low it goes, okay? And this number here is going to help you understand how long it takes him to complete a cycle. How long it takes him to complete a cycle. So I think you understood that from before, but just so that you're on the same page, we'll graph some stuff and then see where everything belongs. And your backup plan is always just going to be plugging in numbers. So I'm going to start by plugging in 0 and see what I get. And I'm going to use my Desmos calculator just so I can plug this in. You can actually plug this in without a calculator. I'll just show you that really quick. So if I was plugging in, let's see, 2 cosine. So 2 cosine of half of 0, right, +4. So the cosine of 0, so the way my brain goes, and this is what we talked about before, 0 is right here. And from the last lesson, we learned that cosine, when we're in the unit circle, cosine was just your x value of that point. So this point is 1, 0. So that means I'm just going to look at this one. So cosine of 0, because 0 times half is 0. So here, this tells me that cosine of 0 equals to 1. So this whole part right here equals 1. So 2 times 1 is 2, plus 4 is 6. So at 0, it's right there. Right? And just so that you believe me, I'm going to type this in on my calculator. 2 cosine 1/2, times 0 and then plus 4, I think. Is that right? Yep, I plugged it in right. And there it is. It's 6. So for those of you who want to depend on the calculator, that's fine. Just to verify, I'm going to encourage you to draw this almost like every single time so your brain gets used to thinking about it. Because in the next chapter, when we go over other things, if you have to always depend on your calculator, you're not going to see the patterns that you're supposed to see. Okay, so the next thing, I don't know, maybe I'll plug in pi because that's a pretty good measure to do. So I'm going to plug in pi. So I'm going to do these by hand just so that you can kind of see. So I'll go 2 cosine of 1/2 times pi plus 4. And so this says 2 cosine of pi over 2 plus 4. And if you think about pi over 2, he's up here. Again, cosine is always going to be your x value. So this is telling me that cosine of pi over 2 is 0, right? That 0 is that 0. Okay. So this is really just 2 times 0 plus 4. So that's just 4. So that guy is landing on my midline. And then I'm just going to continue to plug in 2 pi and see what I get. Let's see, where can I squish some work in here? Maybe here, I'll go this way. So here we'll go with 2 cosine half of 2 pi plus 4. And so this is going to be 2 cosine of just pi, because half of 2 pi is just pi plus 4. And so if I think about where pi is here. His x-coordinate is -1. I don't really care what the y-coordinate is, so I'm just going to look at -1. So this is 2 times -1 plus 4. So that's going to be 2. So at 2 pi, it's 2. And so you can kind of see the symmetry there that's going to happen because it's hitting at the lowest point, right? This told you to find, this told you to find the maximum and minimum. So we already found where our max is, and we're already going to find our minimum. I'm just going to guess here, just looking at this. I'm going to guess that 3 pi is here and 4 pi is here. And then we've completed a whole cycle. Ms. Johnson, how do you know you completed a whole cycle? Because I went all the way around. I went to the highest, I went to the lowest, and I came back, right? Okay, so I'm just going to verify my 3 pi really quickly with you. So 2 cosine of 3 pi over 2, I just multiplied at the same time. So 3 pi over 2 is down here. Again, I don't care what my y value is, but my x is 0. So that's 2 times 0 plus 4. So that's just 4, which is exactly what we got right here. And then last but not least, if you look at this one right here, if I plug in 4 pi, so that will be 2 cosine of 4 pi over 2, which is just 2 pi. So again, I don't care about my y value, but my x value is a positive 1. So that's 2 times 1 plus 4, and that's 6, which is exactly what we got. So there's one complete cycle, or sometimes we call it period, right? So here's one complete period. It looks like this. Remember, this is a wave. It's not a V. So make sure you have curves. And then you can kind of like continue this guy this way. You can kind of continue this guy this way. Just so you can see that complete curve. Okay, so that's all you're doing when you're graphing. The only thing that the only number that you didn't necessarily use or figure out was this half number. And if you think about this half number, it was going half as slow, right? So normally it takes 2 pi to complete a whole cycle for cosine and sine. But if it's going half as slow, that means it's going to take twice as long to complete it. So this half implied that it was going to take 2 times as long to complete 1 period. So our period in this case was 4 pi. Do you see how we completed our whole cycle in 4 pi? So that is what 4 pi is. I mean, that is what a period is. And so now you kind of can use all those numbers to pick and choose how you're going to graph these two, right? Okay. So go ahead and graph those and make sure that you're comfortable with graphing these. We'll be graphing these in class, so I'm not going to show you how to do this here. But I do want you to practice on your own to make sure. So just so that we're on the same page, like you should know what this plus 2 does, right? You should know what this 2 does to your function. And this one kind of looks funny because it says 30 degrees per second. And if you notice, because it says 30 degrees per second, now notice our x-axis is not labeled in radians. It's labeled in like numbers. Okay. So same thing goes down here. You know what you're doing if you can tell me what this 4 is doing. And this is weird, but that pi is doing. What is that pi doing to your function? And notice again, our x-axis is not labeled in radians. It's labeled in numbers because of that pi. Okay, so let's continue on. It says, today you'll be able to apply special right triangles to the unit circle. And are there any angles for which I can find the value of sine or cosine without using a calculator? And the answer now is yes. You will be able to do that. You actually have been doing that for quite some time, but now we're going to put it all together. When we talk about special right triangles, we're talking about those two right triangles. One of them is our 45, 45, 90 triangle, and I'm going to label him in radians this time. So pi over 4, and this was x root 2. Another way you can label this is 1 root 2. I use x because sometimes it's dilated. It means it got bigger or smaller. So I like to use that as well. The other one that is special is your 30, 60, 90, which we will label as pi over 6, pi over 3, and 90, or pi over 2. And then here, this is x, 2x, x root 3, and I'll label it again. This will be 1, this is 2, and this is just root 3. Remember, because we can scale it as big as we want. If you do not have these memorized, again, no problem, but it's going to make your life a lot easier. The equivalent here is like, do you remember when you were in like 4th and 5th grade and maybe you didn't have all your multiples down? That's what's going to happen here. It just makes your life easier. Can you look it up? Sure. But the problem also is that Desmos does not give you exact answers. It gives you decimal approximations. All right, let's continue. So water wheels were used to power flour mills before electricity was available to run the machinery. The water wheel turned as a stream of water pushed against the paddles of the wheel. Excuse me. Consequently, unlike Ferris wheels that have their centers above the ground, the center of the water wheel might be placed at ground level, so the lower half of the wheel would be immersed in the stream. The following diagram shows potential designs for a water wheel. Each of the 12 spokes of the water wheel will measure 1 meter. In addition to the spokes, the designer wants to add braces to provide additional strength. 2 potential placements of the braces are shown in the following diagrams. So here's one of the potential guys right there. Here's another one. Okay. The braces and the spoke to which they are attached form a right angle. So again, this is going to be your right angle. And you're going to be like, yes, right triangles. That means we're going to be using the Pythagorean theorem or sine, cosine, and tangent, right? Okay. So it says, find the measures of angle BAC and ABC in each diagram. Okay, so I'm going to give you a couple seconds to figure that out. This is something that we've been doing, this part here, not new. Okay, so now that you're back, how do we find this angle here? Let's call him theta. How do you find him? So some of you remember from the Ferris wheel problem that because a whole circle is 360 degrees or 2 pi, then we could just divide it by the number of slices of pie that you have. So that's a perfect example. So if you count here with me, and I'll just put little dots just so you know where I'm counting. So 1, 2, 3, 4, 5, 6. So that makes 12 slices of pie. So here I'm going to write measure of angle BAC is equal to 360 degrees divided by 12, which is 30 degrees. Or I'm going to write this as 2 pi divided by 12, which is pi over 6. Okay. So again, remember that the whole circle is 2 pi, like the circumference of this circle is 2 pi. And because our radius is 1, then it's just 2 pi. And then so we get pi over 6. So these are two angles in different languages. Okay, one of them's like English, one of them's maybe Spanish. Neither is better, but I need you to start thinking about things in terms of radians. So I'll be slowly talking to you in terms of radians, meaning pi over 6, instead of just degrees. The sooner you switch over and you're more fluent in radians, again, the easier it'll be for you. All right, so I'm going to do this other one. So the measure, I'll do it over here, of angle BAC. So if we're going with this angle here, right? So it's 1, 2, 3, 4, 5, 6. So it's still 6, but it's just 2 of them. So then this is just 2 times 30 degrees, which is 60 degrees. Or it's 2 times pi over 6, which is just pi over 3. Again, thinking about your different, like, however you calculate stuff. You could have also calculated it different ways, but that's one of the ways that popped out at me. Okay, then it says find the exact lengths. Exact. Okay, so whenever they say this word exact, they do not want you to plug it into Desmos and give me some decimal approximation. Exact answers have radicals in them. Exact answers have square roots. They have logs. They have, what else gives you decimals? Right? It's not it's approximately 0.3. No, like they want exact answers. So they want the exact lengths of AB, AC, and BC. Okay. And they're asking it for both of the triangles. And you might be like, hey, Ms. Johnson, how come these are labeled the same? If you think about it, it should be labeled the same. So let me erase this so you guys can see, right? So in here, we said that this is 30 degrees, right? And in here, we said that this is 60 degrees. Well, if this is a right triangle, what's this angle here, right? And you'd be like, oh, well, it's 180 degrees for a triangle. So that means that this angle has to be 60 degrees because 30 plus 60 plus 90 makes 180. So these two triangles are actually, oops, and then this would be 30, right? So these two triangles are actually the same triangle, just reflected or rotated differently, right? They're sitting in different ways. So going back to our triangle over there, our special right triangles, you should be able to label these, okay? So AB is the length of the spoke, so that's just going to be 1. So AB is going to be equal to 1. So just a little note here, whenever we write AB with a hat on it, that's talking about the segment. If we take the hat off, that's talking about the length of that segment. So this right here is actually telling you the length of segment AB. Okay, so that's what that means, length of segment AB. Okay, so then what's AC then? So if this is 1, and if you look at your special right triangles, or maybe you know them by now, how long is each of those? So the way I like to do it is I like to go this way. Let's see. So I label these guys. This is where my x, 2x, x root 3 comes in, right? So if 1 is equal to 2x, this implies, excuse me, that x equals to 1/2. Sorry, we're fighting a little throat kind of like soreness here. So if 1 equals 2x, that implies that x is equal to 1/2, right? So just divide by 2 on both sides. So that means this is 1/2. So that means BC is 1/2. Then I would just put that 1/2 right there for root 3, and that's what that is, 1/2 root 3. Sometimes I like to write that as root 3 over 2 because it's a little bit easier, so I'm going to actually write that. Let me erase this and scoot that over. So I like to write it like this, root 3 over 2, because it's very clear. And then last but not least, BC was 1/2. Okay. The last thing that they want you to do is label the coordinates of that point. So labeling the coordinates shouldn't be too bad because you're just looking at how far it went over. So that's root 3 over 2. It went over root 3 over 2. Oh, I'm using the same color over and over again. Let me not do that so it'll stand out. Let me go here. Let's use this color. So how far right did you go? I went over root 3 over 2. How far up did you go? I went up 1/2, right? So same thing goes here. How far over did you go? Now this side of the triangle, if you can get your brain to think about this side of the triangle matches with which side? And you're like, oh, it's that one. So it's 1/2 comma. And which side is this side right here? And you're like, oh, it's AC this time, Ms. Johnson. And yep, you're right. So it's root 3 over 2. Okay. All right. So hopefully this is making some sense because all we're doing is we're putting everything that we've learned together. So next it says, based on your working problem 1, label the exact values of the x and y coordinates for each point on the drawing of the water wheel. Remember, the center of the wheel is at ground level, so the points below the wheel should be labeled with negative values, as in the Ferris wheel's model. Label the points to the left of the center with negative coordinates as well. So here you go. It's kind of, I'm going to push this out as really big. You already know this one is going to be 1, 0. We just did this one, right? This one was root 3 over 2, 1/2. And this one right here was 1/2, root 3 over 2. Okay. So now, and then again, this one, it's actually, my favorites to label are the ones that are on the X and Y axes. So go ahead and do that first. And then these triangles are all reflections of the 2 triangles that we just worked on. So you're just going to have to figure out the negatives of them. So that's something that we did work on the last lesson as well. So you should see some symmetry here with some negatives. Go ahead and do that and then pause the video and then come back to me when you're ready. Okay, now that you're back, you should be able to reflect all of these just to make sure that you're on the right page. Okay, so for example, what is the coordinates? I'm going to do our bars first, right? So what are the coordinates here? And you're like, well, it didn't go right or left, so that's 0, comma, and then it went up 1, so it's 1, right? And then so what would this one be? Right? So we went left 1, so that's -1, comma, and then it didn't go up or down, so it's 0. And this one down here is going to be, well, I didn't go left or right, so that's 0, comma, and I went down 1, -1. So similarly, you're just going to kind of do the one with his match. So like here, because we went up 1, it looks like this one, except for we went down 1. So same thing goes here. Like if I wanted to do this one right here, right? Who does this guy match with? And hopefully you say, oh, this guy matches with this because it has the same y value. So that y value is going to be the exact same. So if you can kind of like picture the right triangle here, if you see they're just reflections of each other. So that means the y value is going to be the exact same because you went up. You went up the same amount. So this guy's going to have the √3, the √3/2 as the y value. But notice here, instead of going right half, we went to the left, and left means -1/2, right? So that's that coordinate. And so I'm going to do all of the ones that match this triangle, right? So I'm going to skip this one because this one doesn't look like that one. And I'm going to go, well, that one doesn't, like imagine the triangle, that one doesn't, like reflect this one. This one reflected down looks here, looks like it's here. So I'm going to go here. And if you notice again, it's just a reflection down. Can you imagine that? So we went, x is the same. So we went -1/2, right? But instead of going up √3/2, now we went down √3/2, right? So the next one looks like it's this one. Now you have so much information. You could do a reflection this way, or you can do a reflection this way. It doesn't really matter. So I went to the right 1/2. That makes sense. And then, but I didn't go up √3/2. I went down. So that means I need a big O negative right there. Okay. So now that you saw how I do this pattern, go ahead and pause it and see if you can do that same pattern and verify your answers here. If you already have your answers, just kind of look at your answers to see if they match that. All right, so now that you're back, I'm going to use this pinky color, and I'm going to erase these triangles. Oops, I'm not erasing anything. I'm scribbling. There you go. So I'm going to pretend that I see this. Oops. There you go. I'm going to pretend that I have this triangle here. Now notice I'm going to have the one that reflects down, the one that reflects across, and then that one that reflects down. So I'm going to do all of those. Now I'm going to do it in the same exact manner. So notice I go left this much. So it's not going to be positive √3/2. It's going to be negative, comma. And I'm going to go up the same. So that's going to be the same, 1/2. Excuse me. So same thing goes here. I'm going to go left again. So that's -√3/2. But instead of going up 1/2, I'm going to go down 1/2. So that's why it's -1/2. And then same thing goes here. I'm going to do the same thing. I'm going to go right that much. That's the same. So this is going to be √3/2, comma, and then instead of going up 1/2 to get here, I'm going to go down. Down means negative. And so here's part of your unit circle. So if you ever Google unit circle, you'll see this, but there'll be a couple more that you're missing in here. But this is pretty much your unit circle. You can build this every single time as long as you know your 30, 60, 90 triangle. The only thing I used here was the fact that I knew that if I go left, it means negative, and if I go right, it means positive. Up means positive, and down means negative. And because of this, right, because I knew this right triangle here, this guy right here, I was able to fill in that whole thing. Okay. Some teachers have you memorize the unit circle. I'd rather not. I'd rather you know how to build it. Okay, because you can just Google unit circle and then boom. So how do we read this thing? Okay, so how do we read this thing? So the first thing that I'm going to do is it says look for, okay, so use the diagram in problem 2 to give the exact values for the following trig expressions. So the first thing that I'm going to do is it says sine of pi over 6. And so there's 2 ways to do this. I'm going to show you both ways. You figure out which way you like better and then do that way. Okay. So the first thing that I do is I want to find out where pi over 6 is. And if you remember, pi over 6 was one of the slices here. So this angle in here is pi over 6. And since it's asking for the sine, right, and I know that this is 1 unit, I just need to grab the y coordinate. So here, I'm going to tell you. So y coordinate, because I'm looking for sine, right? And so the y coordinate is 1/2. And that's it. That's all I do. Okay. Okay. I'm going to show you a different way using sine of 5 pi over 6. I'm going to show you a different way. Oh no, the same way, sorry. Because this way was right here. So 5 pi over 6 looks like this. So I'm going to count 5 slices of that pi. Okay. So I want 5 pi over 6. So here's 1, 2, 3, 4, 5. So it's this guy right here. Okay. So I'm going to go like this to show you. This is 5 pi over 6. Right. And again, because it's sine, I just want the y coordinate. So that's just 1/2. Okay. So that's pretty much it. So this is how you read this unit circle. So if you're using the unit circle, this is how you would read it. In your brain, you know that sine is the same as the y coordinate, and cosine of that angle is the same as the x coordinate. So I'm going to show you a different way using this cosine one, just so that you and I are on the same page, okay? So 7 pi over 6. So I still am thinking about this thing here, and I'm counting 7 pi's over 6. So this is what it looks like for me. So because this is 6 pi's over 6, right? That's 6 pi's over 6. It means I have 1 extra pi over 6. So I draw that in there, and I say that this is 7 pi over 6. Okay. So I could either go over here and steal that x coordinate, or I can go this way. Now, this is for the people who have memorized your 30, 60, 90 triangles, and you want to use that. Okay, so because I know this is pi over 6, I know that this is a 30, 60, 90 triangle. So what I'm going to do is the very first thing is I draw my angle, and then this has to do with what we were talking about before. Then you draw your triangle, then you label your triangle. Now, because this is a 30, 60, 90 triangle, and here's your pi over 6, you're going to label it as x, 2x, and x root 3. Okay? Except for now, you're going to make sure that the signs are all the same. In order to get here, notice I went left. So that means I have to go with a negative sign. This is a negative. And I went down, so that's another negative. Okay? Your hypotenuse will always be positive, so don't worry about him. And then now you're just going to find the cosine of this reference angle. So the cosine of this guy is, if you remember, it's adjacent over hypotenuse. So that answer is going to be negative x root 3 over 2x. The x's will cancel, and then you're left with negative root 3 over 2. Now look at, that's the same exact thing you would have gotten had you counted over 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, and then look at the x coordinate. It's the same. So it just depends on what you like to do. If you have access to your unit circle, you're just going to be reading this thing over and over again. For me, I think the reason why I like drawing it over and over again like this, it gives me that like understanding that I didn't copy my unit circle wrong, or I'm paying attention to the signs, and I'm really using the tools of the 30, 60, 90 and SOHCAHTOA. Okay, so you're going to go ahead and you're going to fill out the rest of these and make sure you understand all of these. We'll go over these answers in class. Notice that 3 pi over 2 is going to be a little bit different, and 7 pi over 3 is going to be that. So let's do sine of 7 pi over 3 using our thing. So 7 pi over 3, remember, it's this guy. Remember, this was pi over 3 over here. Let me go with this guy here. This triangle here was pi over 3. So you're going to go to this one, pi over 3, 2 pi over 3, 3 pi over, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi. I'm just skipping one every single time. 6 pi over 3, and then this is 7 pi over 3. So this is where 7 pi over 3 is. So going back here, they say, hey, can you find me the sine of 7 pi over 3? Well, the sine of 7 pi over 3 is just going to be root 3 over 2. Okay, so the other reason why I like doing this as well is if you notice when I was counting, I was a little bit off. So if I start counting, if I look at how many whole pies is 7 pi over 3. So this is 3 pi over 3. This is 6 pi over 3. And then I get a little bit more with 7 pi over 3. And so that's what my triangle is going to look like. And then I would label it. I get the same exact answer. So this is, let's see, this is 1, 2, and this is root 3. Sine of that is going to be root 3 over 2, which is exactly what you guys got over here. Okay, same thing. So which way do you like better? I would practice both, especially those of you who don't know your 30, 60, 90s. It's really good to make sure you memorize those or like use those. Okay. The next part, it says, here's a plan for an alternative water wheel with only 8 spokes. Label the exact values of the X and Y coordinates for each of the following schematic drawings of the water wheel. Hint, you may want to begin this work by finding the length of the brace shown. So this is the same thing, except for now we're dealing with the other special right triangle. And you would have known this because you would have divided, right? You would have went 360 divided by 1, 2, 3, 8, which is 45 degrees. And I'm going to go 2 pi divided by 8 is pi over 4. So these two are the same thing in different languages, right? So the next thing that I want to make sure that I do, hold on, I just need to check something. Okay. Okay. So the next thing that I want to do is I just want to label everything. So if you remember, if this is one in our 45, 45, 90 triangle, then this is our, this is x, x, x root 2. So if 1 equals x root 2, and I'll do the math over here. If 1 equals x root 2, and then you divide out, you get x is equal to 1 over root 2, which is not acceptable in some places. So we have to rationalize our denominator by multiplying by root 2 over root 2, right? So that just equals to root 2 on the numerator. And the denominator is root 2 times root 2, which is root 4, which is just 2, right? So then this is equal to root 2 over 2, and this is equal to root 2 over 2. So again, if you look at your coordinates, right, you look at your coordinates, you're getting root 2 over 2, root 2 over 2, which is nice because they are the exact same. So go ahead and label all of these, and then go ahead and do all of these. And then we'll check answers during class to make sure everybody's on the same page. Okay, so it says during the runoff, the spring runoff of melting snow, the stream of water powering this water wheel causes it to make one complete revolution counterclockwise every 3 seconds. Okay. So hold on, let me grab something. Okay. So during the spring runoff melting, so the stream of water powering this wheel causes it to make one complete revolution counterclockwise every 3 seconds. So it goes around and it's 3 seconds, around 3 seconds. So it's going pretty fast. Write an equation to represent the height of a particular paddle of the water wheel above or below the water at any time t after the paddle emerges from the water. So write your equation so the height of the paddle will be graphed correctly on a graphing calculator in degree mode. Okay, so because you're looking for the height, right? So can you imagine my water wheel? Here's my water wheel. And then they want to know the height of this water wheel, which means this distance here, right? If you continue this out like this, right? The distance above the water, which mode are you in? Are you in sine or are you in cosine? So hopefully you said sine, because sine uses the y coordinate. So I'm going to be using sine. So this is going to say sine something, right? And so we'll use h of t because that means the height. So it's just the sine of something. Now, the only other information that they gave us was that every 3 seconds, it does a complete revolution, right? It does a complete revolution. So that means I need to know how far is it going? How far is that one paddle going every second? So looking at this, let's pretend we start our paddle off right here. If it's going to finish this whole thing in 3 seconds, how far did it travel in 1 second? And maybe you're thinking, oh, I just got to divide by 3. Exactly. So when you divide this by 3, like I think I'm a pretty good pie cutter. Maybe not. I don't know. Right? It goes that far. Right? And they told us to find it in degree mode. So then I'm just going to go 360 divided by 3 is 120 seconds. So that means that number goes here. 120 times t is going to be our function. Does that make sense? And I'm going to do the same exact thing, except for instead of using 360, I'm going to use 2 pi. So I'm going to go 2 pi over 3, and I'm going to leave that as my thing. So it's going to be h of t equals to sine of 2 pi over 3t. And that's it. Okay. So this last question is asking you to do this one last problem. So I kind of want you to do this one on your own and see if it makes sense to you. And we will check this in class. Okay. And then our takeaways, we will also go over in class. And hopefully this makes sense to you. Have a great day.